Okay, so let's tackle two more problems. The first one, you're given a rooted tree. So you're given a rooted tree with n nodes. You're given the tree, and we perform some process on this tree. What we do is we select a node at random, and then delete that node and the whole subtree as well. Okay? We do that until all nodes are removed. The question is, what's the expected number of moves before everything is removed? N is up to 10 raised to 5. What? The 3 will be input. Yeah. Okay, any ideas? Yes?
For every element, we can define x, like similar to the previous problem, we can define xi to be 1 upon size of subtree of which, from which it gets removed.
For which it gets removed?
Yeah.
Okay, and then?
And then we need to realize.
So how do you compute the expected value of this? Okay. So that's one approach. Can you think of anything else? So in this problem, I think it is possible to do it this way, but I haven't checked, but it will probably be quite difficult. But let me show you an elegant solution to the problem. So let's say you have a tree. So in this case, you have some tree. And let's look at a particular node. At some point, it will get removed, right? So when will it get removed? It will get removed if one of these nodes are selected, right? If we select this, the whole subtree, including it, will be removed. Okay? So now, let's consider some sequence of moves. The first time some node is removed from this path, this node will get removed, right? So what's the probability of this node being selected in some sequence? So we're defining x sub I as the probability that node I gets selected in our sequence. Yes. So let me be clear. X sub I is the probability that the ith node is selected in our sequence. So the number of moves in our sequence will be x1 plus x2 plus dot, 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 up to x sub n, right? Because the probability of a node getting selected, I mean, this is not the number of moves, but the expected number of moves, right? Because the probability of a node being selected is equal to the expected number of sequences where it is selected. Okay, is that clear? It's the reverse of the thing we derived earlier. If you have a variable, so let me, I think I stated that wrongly. Let's just say x sub I is 1 if node I is selected in our sequence, and 0 if not. Okay? So this sum will be the number of elements selected, or in other words, the number of moves before everything gets removed, right? Is that clear? Now we want to find the expected value of this. So it's similar to the previous problem now. But let's say by linearity of expectation, we simply have to look at each x sub I. But let's say this is node I, and we're asking what's the expected, what's the probability of it being selected. Consider all sequences before some node in this path is removed. Before any node in this path is removed, node I is still here. But the first time some node is selected from this path, node I gets removed, right? And each node is equally likely to be selected as the next one, regardless of how the sequence went outside, right? So what's the probability of node I getting selected given that information? It's just 1 over the depth of I, okay? Where we count the depth of the root as 1, okay? So the expected value is 1 over the depth of I, where depth starts at 1. So the answer is simply the sum of the 1 over depth for all depths, right? And that's easy to compute in O of n. And that's pretty neat and somehow magical as well. The usage of expected value sometimes feels magical, right? Any questions? And now let's leave with the final problem. Okay, in this problem, you have n points on a plane. Okay. So what we do here is first, for each point with with 1/2 probability, we remove it. Okay, so we are left with some number of points, possibly still all of them, possibly none of them. Okay. The question is, what's the expected area of the convex hull? And n is up to 50, I think.
Like convection of
What?
since we are removing the point to convection.
So there are n points. With 50% probability, we remove each one of them. Okay. What's the expected area of their convex hull, of the remaining points? That's the question. Yes?
Average of the areas of all convex hulls formed by 25 points. It's not an algorithm, but if you just choose all the different possible points of 25, calculate the area, will that?
How many points do we remove?
There's no fixed number of points to remove. Okay, I'm saying there are up to 50 points, and we look at each one of them, and with 50% probability, we remove it. Okay, so it's possible that you end up with 25, but it's also possible to end up with 40, 50, even none of them. Okay. Yes.
Try to measure for each triangle the expected contribution of this triangle to the area of the convex.
What triangle?
For each triangle that you can form by selecting 3 points from the input.
Okay.
Try to measure how much the expected value of this triangle's contribution to the area.
But how can you ensure that if you have a triangle and you have another triangle, you take into account their overlap and don't count that twice? Right? How much what?
How much is the value 2 power 50?
How much?
Is the value 2 power 50?
The what?
2 power 50.
What is?
So how many digits is it? 9, 10, 11.
How many what?
Now number of digits.
The number of digits. You can estimate 2 raised to 10 as 3 digits. So this is going to be 15 digits. 16 probably. So obviously you cannot enumerate all subsets and find the convex hull of each. You want a hint? You want a hint? So a hint is a shoelace formula. Remember shoelace formula in one of the previous lectures in geometry? So if you have a polygon like this, so how do you compute the area of some polygon? Right, you traverse in some order, let's say counterclockwise, and then for each edge, let's say the origin is here, compute this triangle area, right? And depending on the orientation, it will be positive or negative, right? So this one will contribute this, but this one will cancel out some part of the area. But after doing it for all edges, you will end up with exactly the area you're looking for. So that's the hint. Yes?
For every pair of points, if we can find the probability of it being the convex hull, then we can take its respective times the area of the expected value.
Okay, that's good. We're saying for every pair of points, we calculate the probability that it ends up in the convex hull, and then somehow manage to add up its contribution.
Yeah, then we will multiply by the contribution and then
Okay, I think that's correct. That's basically it. So for every pair of points, let's say you have a bunch of points, and you want to consider this. Okay? So in the area, in the shoelace formula, the contribution of this, assuming it belongs to the polygon, is the area of this triangle. But it also depends on the orientation. If it belongs to, if you do the traversal this way, it's a counterclockwise order, then the contribution will be positive. If it is this way, it will be negative. So let's just assume that you do it this way, okay? You can do the same thing by just looping to all pairs. You'll consider each pair both in both orientations, okay? So let's just assume you're traveling it this way. Now we want to compute the probability of it being in the convex hull. How do you do that?
ignore the points on the right hand side.
Yes, you ignore these points. Actually, you have to compute the probability of them being removed. Right? That's important. So just count the number of points here, and then you raise 0.5 to that power, and then add the contribution. That's it. Add everything. Everything works using linearity of expectation. All right? So that's another application of linearity of expectation, and it still feels magical, especially if it's hidden sneakily like that. All right?